In this session, we'll break down transformer attention weights in a way that's actually useful for practice. We'll go from the math and paper notation to how attention is implemented in real production code. If you're building LLM systems or preparing for AI and LLM engineering interviews, this is meant to give you both the intuition and the practical understanding you need. Here's the roadmap for this session. First, we'll cover the core attention formula and clarify where the WQ, WK, and WV projection matrices actually come from. Then we'll connect that theory to practice by looking at how PyTorch and TensorFlow implement it. After that, we'll inspect a real model, including BERT and Hugging Face code. Finally, we'll wrap up with interview-ready explanations and practical career signals you can use right away. Here's the multi-head attention formula from the original transformer. The full attention output is built by combining several heads, and each head runs its own attention over the same input. The important detail is that WQ, WK, and WV are trainable weight matrices inside the attention layer itself. They're learned as part of the model, not separate token lookup tables defined somewhere else. Where do Q, K, and V actually come from? Not from the raw input directly. The attention block first takes the input representations and passes them through 3 separate learned linear projections. Those projected versions become the queries, keys, and values. This matters because attention doesn't operate in the original embedding space. It works in a learned matching space designed to help the model compare tokens and decide what information to pass along. Here's the key mental model. Attention involves 3 distinct roles. First, we start with the raw input, like token embeddings or hidden states from the previous layer. Those are the original representations. Next, the model applies 3 learned linear projections, WQ, WK, and WV, to produce queries, keys, and values. Finally, attention scores are computed from queries and keys, and those scores are used to mix the values into the output. Here's the key difference between self-attention and cross-attention. In self-attention, the same input tensor is used for queries, keys, and values, but separate learned projections turn it into different Q, K, and V representations. That's what allows the model to compare and combine information in different ways. In cross-attention, the query comes from one sequence, while the keys and values come from another, again, using learned projections to align the two. PyTorch provides multi-head attention as a built-in module called MultiheadAttention. You set the total embedding size with embed dim and choose how many parallel heads to split it into with num heights. When you call the module with query, key, and value, it returns both the attention output and the attention weights. Internally, the in-project weight parameter combines the learned query, key, and value projection matrices into one fused tensor. In TensorFlow, the Keras multi-head attention layer handles the projection steps for you. Query, key, and value aren't used directly. They're first passed through internal dense layers that learn the WQ, WK, and WV projections. Here, we set 8 heads with key dim and value dim, defining the per head projection sizes. Then calling the layer on query, key, and value returns the attention output, all with the projection logic built in. This slide compares the multi-head attention APIs in PyTorch and TensorFlow. The underlying math is the same, but the interfaces look different. In PyTorch, you use NN, NUA, multi-head attention, with embed dim, fused projection weights, and an out project layer. In TensorFlow, multi-head attention exposes key and value dimensions separately and uses separate dense projections. Both can also return attention weights or scores when needed. Here's the concrete version, inside a real model. In Hugging Face's BERT with space, the BERT self-attention module contains 3 standard linear layers: query, key, and value. Each mapping 768 features to 768. Those layers are the actual WQ, WK, and WV matrices. They're not symbolic objects. They're ordinary model parameters, created when the model is built and then learned through backpropagation during training. One practical skill in production is recognizing that attention layers use different names across model families. In BERT-style code, you'll usually see query, key, and value, like in BERT self-attention. In GPT or llama-style models, those often appear as QProject, KProject, and VProject, which makes the projection step more explicit. Then, after all the heads are combined, the output projection is typically named out project or OProject. This matters for fine-tuning because the attention projection layers are usually the first place we intervene with methods like LoRa, adapters, and other PEFT approaches. They're explicit, trainable modules, so they're easy to target. If you know each projection is a 7-delayed GCI by 7-delayed GCI linear layer, you can estimate parameter counts, understand head structure, and decide what to freeze. And if you can identify these layers by name, pruning and distillation become much more precise. Here are 3 common questions with straightforward answers. First, WQ, WK, and WV are learned projection matrices inside each attention layer. They're initialized when the model is created and updated through backpropagation during training. Second, Q, K, and V are not the raw input embeddings. The inputs are transformed into those spaces first. And third, self-attention can reuse the same hidden states because different learned projections produce different roles for queries, keys, and values. When hiring managers assess attention knowledge, they're looking for more than memorized formulas. Strong candidates can explain the math, then point to exactly where it shows up in code. They can track tensor shapes clearly, know there's an output projection after concatenation, and connect the paper's notation to real framework APIs. Common mistakes are staying too abstract, mixing up token embeddings with Q, K, and V projections, or missing those projection layers entirely in implementation. This portfolio project is where you prove the concept end to end. In the first notebook, you'll use PyTorch to pass a tensor through MultiheadAttention, track the shapes, and show how embed dim is split across heads. In the second, you'll recreate that in TensorFlow and compare the APIs and projection behavior. In the third, you'll inspect a pre-trained Hugging Face model and locate the actual query key and value projection layers. Here are the key dimensions to know code for BERT base. The hidden size is 768, and each of the query, key, and value projections is a linear layer that maps 768 to 768. Attention is split across 12 heads, so each head gets 64 dimensions. And there are 4 projection matrices total: WQ, WK, WV, plus WO, the output projection applied after concatenating the heads. A strong career strategy is to build leverage, not just breadth. For each key idea, map it all the way through, from the paper's notation, like WQ, to the API, like NNW's linkNew, to the actual model component, like BERT disadvantaged canalier, detention W self solve query. Then, turn that understanding into compact, concrete artifacts. One notebook with shape traces and 1 inspection script is far more convincing than 10 slides that just claim you understand transformers. Here's the bottom line. The query, key, and value matrices are not external inputs. They're learned inside the attention layer through its own linear projections. That's how the original paper defined WQ, WK, and WVI, how frameworks like PyTorch and TensorFlow implement them, and how models like BERT expose them as NL-lang-Neag parameters. If you can explain that clearly and show it in code, you're demonstrating the level of understanding hiring teams look for. Here's a quick cheat sheet for attention. WQ, WK, and WV are the learned projection matrices, usually implemented as linear or dense layers. Q, K, and V are the projected outputs of those layers, not the raw embeddings. In self-attention, the same source tensor is projected 3 different ways. In cross-attention, the query comes from one sequence, while keys and values come from another. Wo is the output projection after concatenating heads, and head dim is just embed dim divided by numHates. You're ready to build? At this point, the key idea is clear. WWT, WT, WT, and WWT are learned projection matrices inside the attention layer, not separate embeddings. From here, read the docs until the PyTorch and TensorFlow MultiheadAttention APIs feel familiar? Then inspect real Hugging Face models and locate those projection layers by name. Finally, ship it with 3 hands-on notebooks, one in PyTorch, one in TensorFlow, and one for model inspection.